here at the University of Amsterdam. In this module, I will tell you something about the principles and practice of economics, using the first 4 chapters of the book by Acemoglu, Leibson and List. Before I do so, however, let me explain to you why, historically, economics got a bad name. In the late 18th century, there was a philosopher by the name of Thomas Malthus. Malthus had a theory. His theory was that food production would grow linearly, while the population would grow exponentially. People got many kids at the time. He thus predicted that food would run out and that a majority of people would live on the edge of starvation. Because of this prediction, economics got to be known as the dismal science. In the 3 videos that you are about to see, I hope to prove you otherwise. I will try to do so using 3 principles: optimization, equilibrium, and empiricism. These can be seen as the core principles that economists use to study people's choices and how those choices affect society. The first principle is optimization, which is the idea that people try to choose the option that makes them happiest among all things that they could possibly choose. The second principle is equilibrium. When you put many optimizing people together, some kind of equilibrium situation will arise. A situation where I do not want to change my behavior given what you do, and you do not want to change your behavior given what I do. The third principle is empiricism. Nowadays, economists can justify their claims with data much more than we could in the past because of increased digitization. I will discuss equilibrium and empiricism more extensively in the next videos. In this video, I will give you some examples of optimization, choosing the best you can. Chapter 3 shows an interesting example of optimization, choosing where to live. An expensive apartment close to the city center, or a less expensive apartment farther away. This is a trade-off between cost and distance, or cost and time, if you realize that higher distance requires a longer travel time. Consider Michelle. Michelle is a student who is about to join the business administration program of the University of Amsterdam. Michelle has to decide on an apartment to rent. The apartment should be at a suitable distance from the university. Assuming that each hour spent commuting implicitly costs her $10, she will choose an apartment that has the lowest combined commuting costs and rent for the apartment. In this example, she will choose to live far from the university. If she valued time more than $10 per hour, she may decide to live closer by. Now you may wonder whether people really optimize. Surely there are many factors at play, many of which people have no way of factoring in. Consider the graph plotting apartment prices in Portland. The graph shows an interesting pattern. Indeed, rents drop for apartments farther away from the center. There is a strange flat part to the graph, however. What can explain it? The motorway that circles around Portland. Because of that motorway, the travel time for people that live 9 to 15 miles from the center is about the same. This shows that people must be trading off rental costs with travel time in some way. They are optimizing. Let us consider another example of optimization using a simplified model. Economists like to use models to illustrate important economic mechanisms. In this case, imagine you are a manager in a fishing company. How many boats and crew should the company use to catch fish on a lake? The company can rent a boat and crew for cost C per boat and sell each fish that it catches for price P. The number of fish that it can catch is determined by a function f of the number of boats B. Then it is easy to write down the profit of the fishing company pi as a function of B. This is total revenue R minus total cost C, where revenue is price times a function f and total cost is small c times the number of boats B. If the firm uses more boats, it will catch more fish. But there is a catch. The more it fishes, the harder it gets to catch extra fish. This is because they become harder to find, mainly because the firm is hurting the reproductive capacity of the fish, and the fish stock diminishes over time. Therefore, the function f bends downwards. An example of such a production function f is given at the bottom of the slide. If each additional boat gives less extra fish, productivity per boat must drop. That is what this graph shows. If the firm has just one boat, it might catch 2% of the fish in the lake, while 50 boats would only catch 1% per boat. The average production function is given at the bottom. It is simply f divided by b. Given the fishing technology, we might ask how many boats you will use when optimizing. Will you use 20 boats or maybe 40? On this slide, we assume that the price is 450 and each boat costs 4. The blue line shows average revenue, so V times P. The orange line shows marginal revenue, which is the additional revenue each extra boat gives. Both lines start at the same point, at 9 per boat, but marginal revenue then drops faster. At 25 boats, marginal revenue is equal to marginal cost. It turns out that profit is largest at this point. This is because as long as additional boat gives more additional revenue than cost, profit goes up. So you have a good reason to expand the fishing company's fleet until the orange and green lines cross. There the red area is as large as it can possibly be. Profit is maximized. The previous illustration shows how we can find the fishing company's optimal choice of boats graphically. We can also do so mathematically. To find the maximum of the profit function, we need to set its derivative equal to 0. This means marginal revenue minus marginal cost must be 0, which is the same as setting them equal, as we did in the figure before. Using the production function f that was given, we can solve this equation to get the optimal choice of boats, B star. This is at the bottom of the slide. With prices equal to 450, a marginal cost of 4, we can use the formula to find the optimal number of boats, 25. Also, we can calculate how many fish is caught, 1/3 of the lake, which gives a fishing company 50 in profits. Maybe more important than these calculations is the insight that the model can help us predict how the fishing company will respond if the price of fish changes or if costs change. These predictions may be important when considering overfishing, to which we will turn in the next video. If you want to know more about optimization, in particular how people respond to monetary incentives, click on the video by Cowan and Tabarrok. In preparation for the exam, you can do the selected questions of Chapter 3 and check out these slides again to see if you follow all the steps.